Well, folks, I have the series circuit set up like a ski lift, what I was talking about today in class, kind of like you're at White Hills, and we have a 30-volt source that's giving 30 joules of energy per coulomb of charge. So just like a ski lift will energize you by carrying you from the bottom of a hill to the top of the hill, giving you lots of gravitational potential energy, a battery, by pushing the electrons into the wire, is giving them potential energy, the ability to do work as well, to the tune of 30 joules per coulomb. That's what the voltage means. It's the number of coulombs, the number of joules per coulomb of charge. So we have a 30-volt, gain for the electrons, and then when they pass through the 10 ohm resistor, there's a 10-volt drop. That means that they dissipate or transform 10 joules of energy per coulomb as they pass through, and that might turn into it could turn into heat, it could turn into mechanical energy, it could turn into sound, light, anything like that. If you're a skier, it's going to turn into carving up the snow, right? Like, I mean, digging into the snow, that actually turns into heat over time, right? I mean, that's what contributes to snow turning into ice, all of the stopping that occurs on it. So a 10-volt drop there, and then when we come across here, we have a 15-volt drop. So now we get 25. And then when we come across here, we have a 5-volt drop, and lo and behold, we have a 30-volt drop as you go around the circuit. Now, if I change that 30 volts, let's bring it down to 15 and watch what happens. You can see here that the voltage has changed. A 15-volt gain, now you have minus 2.5 through the third resistor. You've got minus 5 through the first resistor, and you've got minus 7.5 through the second resistor. It adds up to 15. So no matter what the voltage gain is, by the time the electrons go around the circuit, they will lose all of that energy, just like a skier. Like you're up at the top of the slope, you just get out of the chairlift, but by the time you go down through the different runs and you stop multiple times digging in your skis, by the time you end up down at the ski lift again, all of your energy is gone and you're ready to go around again on the circuit. So it's a very useful analogy, actually. So the voltage drops must equal the voltage gain, and the total amount of voltage in any circuit is zero. Gains, drops. Just like like when you're skiing. You don't go home with energy. You don't go home with energy stored in your body. You use it up every time you go around the circuit. The current here is 0.5 amps, and it doesn't matter where I sampled it. It can be in the resistors, it can be in the wires. Doesn't matter, it's always 0.5. So I have this screenshot here of that scenario set up. And you know what? I'm going to draw a little skier here. That's something I forgot to do. So I'm going to put a skier here at the top of the hill. So there you go. And ready to carve up the slopes. Helmet on for safety. Safety's number one priority. And here you are. Let's put some longer skis. And there you go, down the ski slope. And you've got all your energy from the battery or from the ski lift bringing you up there, and now you ski down through, and you're losing energy as you go down through each one of these different runs. If we want to find out the current in this circuit, the way that you do it is this. So the current is the voltage, the total voltage, divided by the total resistance. Some people figured this out in class today. I know a lot of you are kind of playing around with the different things, putting different things in the circuit. But if you managed to get this far, you would have come across this realization that the current is equal to your voltage from the battery divided by your total resistance, and here it's 10 plus 15 plus 5, which is 30 ohms, and that's 0.50 amps. And that's what we measured when we went around here. So there your I is 0.50 amps, and it's flowing this way, flowing that way, right? And it doesn't matter where you measure it, you're going to get the exact same the same reading. The other thing that we came across, or that we figured out, or some people figured out, is that the voltage drops are going to equal the voltage gains. And so the voltage drops, the V1, which is across R1. Now you see this equation here, I is equal to V over R. Current equals voltage divided by resistance. If you rearrange this equation, you get voltage equals current times resistance. Just cross multiply. So when we look at the first resistor, we have 0.50, that's the current. The resistance is 10, and we get a drop of 5.0 volts. Now, you can call that a voltage drop, or you can call it negative 5 volts. Normally, we don't call it negative. It's just understood that these are drops, and so putting the negative in front of it just becomes redundant. So you can just call it a voltage drop of 5 volts. The V2 is going to be I, and the I here is the same everywhere, so we don't need to worry. It's the same I. And so this is going to be 0.50 times 15, which would be 7.50 volts. That's a drop again. And the V3 is going to be I times R3. And we measured this, right? Is going to be the 0.50 times 5.0 ohms. And that comes out to be 2.50 volts. And this is what we measured with our voltmeter. 5 volt drop across the 10, a 7.5 volt drop across the 15, and a 2.5 volt drop across the 5. And obviously, if we change the voltage in the battery here, that's going to change the voltage drops across the resistors because the current is going to increase. So that's these are the fundamentals of series circuits.